So now we will discuss computation on arrays broadcasting. Saving the file by the name, broadcasting. So we saw in the previous lectures how NumPy's universal functions can be used to vectorize operations and thereby remove slow Python loops. Another means of vectorizing operations is to use NumPy's broadcasting functionality. Broadcasting is simply a set of rules for applying binary ufuncts, which are addition, subtraction, multiplication, etc., on different arrays of different sizes. So let's introduce broadcasting. Recall that for arrays of the same size, binary operations are performed on an element by element basis. Starting off as np is equals to np dot b is equals to np dot a plus b. That gives the answer array 567. So broadcasting allows these types of binary operations to be performed on arrays of different sizes. For example, we can just as easily add a scalar. Think of it as a zero-dimensional array to an array like this, a plus 5, like this. We can think of this as an operation that stretches or duplicates the value 5 into the array 555 and adds the result. The advantage of NumPy's broadcasting is that this duplication of values does not actually take place, but it is a useful mental model as we think about broadcasting. We can similarly extend this to arrays of higher dimension. Observe the result when we add a one-dimensional array to a two-dimensional array. Starting out, m is equals to np dot ones, 3. This results in this 1 1 1 1. Now m plus. This results in 1 2 3 1 2 3. Here the one-dimensional array A is stretched or broadcast across the second dimension in order to match the shape of capital M. While these examples are relatively easy to understand, more complicated cases can involve broadcasting of both arrays. Consider the following example. We are going to show you here np dot range b is equals to np dot range the bracket 3. Now open up the square bracket, colon, np dot new axis, print a, print b. Now this results in this 0 1 2, then 0 1 2. So now a plus b, this results in 0 1 2 1 2 3 2 3 4. Just as before we stretched or broadcasted one value to match the shape of the other, here we have stretched both a and b to match a common shape, and the result is a two-dimensional array. The geometry of these examples is what I'm going to show you here. So let me show you a visualization of NumPy broadcasting, as you can see here. So the light boxes represent the broadcasted values. Again, this extra memory is not actually allocated in the course of the operation, but it can be usefully conceptually to imagine that it is. So now let's discuss rules of broadcasting. Broadcasting in NumPy follows a strict set of rules to determine the interaction between the two arrays. This is rule number 1. This is rule number 2. Then we have rule number 3. So rule number 1 states that if the two arrays differ in their number of dimensions, the shape of the one with fewer dimensions is padded with ones in its leading left side. Rule number 2 states that if the shape of the two arrays does not match in any dimension, the array with shape equal to 1 in that dimension is stretched to match the other shape. Rule number 3 states if in any dimension the size disagree and neither is equal to 1, an error is raised. So to make these rules clear, let's consider a few examples in detail. Let's discuss the broadcasting example number 1. Let's look at adding a two-dimensional array to one-dimensional array, starting with m is equals to and b dot ones is equals to and b dot arrange. Now let's consider an operation on these two arrays. The shape of the arrays are m dot shape is equals to 2, 3, and a dot shape is equal to 3, and it goes on. So we see by rule number 1 that the array has a few dimensions. So we pad it on the left with ones, like this. By rule number 2, we can see that the first dimension disagrees, so we stretch this dimension to match this. And the shapes match, and we will see the final shape will be 2, 3. Now, plus arrays 1, 2, and 3. Now, broadcasting example 2.